And welcome back, AP Calc AB students. Time for more FRQs. This question is from the AP exam AB from the year 2015, and this is question number 1. And since it is number 1, this is a calculator-based question, but it is also the style that falls under the pattern of 2 rates. So we're going to have a rate in and a rate out and an initial value probable or amount more than likely on these types of problems. So let's read the question, get a feel for it, and we will see what we can do. So the question says, the rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t is equal to 20 sine of t squared over 35 cubic feet per hour. T is measured in hours, and the range is 0 to 8 inclusive. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by d of t, negative 0.04 t cubed plus 0.4 t squared plus 0.96 t cubic feet per hour for the same amount of time. There are 30 cubic feet of water in the pipe at time t equals 0 when the day begins. So I'm just going to sketch a diagram of what's going on here. So we probably have a pipe. It's got a little bit of an incline or decline to it, and we'll say maybe it's just a round pipe like this. And so what's going on is it's raining, and maybe this is the ground here, and they're trying to get some rainwater to disperse down below. Okay, and so maybe there's a path or something over here. But as the rain is coming down, as the rain is collecting, the rain is entering the pipe, and that is the r function. So the rate the water's going in is the r function. Well, just after maybe leaves or dirt or who knows what, there's a mound of stuff in here that's gotten a little bit clogged, and so the water doesn't just go straight through, it backs up. And so as the water flows in here, you could kind of imagine it kind of makes a little bit of a dam if you thought about it this way. So the water has to rise and get over this little mound, so the water keeps rising, and then it's able to go out, and then it flows out. So it flows out at the rate of d. So if we were to imagine whatever this mound here of dirt is, we'll make this really dark. The question says that before the water starts flowing, it says there's already water in the pipe that's stuck here behind this mound. Probably would be the case if you've ever seen in a partially clogged drain. So this amount, according to the problem, it says that there's 30 cubic feet of water in the pipe before anything begins that never gets to drain out. So this is how much is left after the rain. So it rains, goes in at r. There's 30 in here, and when it crests this, then it comes out at d. So rate in, rate out, initial amount. And what we're going to have to do is figure out stuff like how much water flowed in the pipe, how much water flowed out the pipe, how much water is in the pipe at any given time, etc. And that's the nature of the question. So you can kind of think of this situation. This is what we're dealing with. And now we will see what we can figure out. So part A of the question says, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval from 0 to 8? Well, once again, what do you get when you integrate a rate? Whatever the rate produces. So it's giving us the rate that the water is flowing in. So it says how many cubic feet flow in. Just integrate the rate that it flowed in. So usually A tends to be a little bit on the easier side, and you just say, well, I'm just going to integrate the rate it flows in from the time they want it, from 0 to 8, and that's going to be the function r of t, dt. Now, this is a calculator question, plus it's a sinusoidal, and so we're going to take advantage of our calculator here. Now, I'd already put this in earlier, and so I have this here. So you can see I'm integrating from 0 to 8, and there is the 20 sine of x squared over 35 dx. In the calculator, it's x, and that's what I have here. So we'll let the calculator do the work, and we're getting 76.570. 76.570, and let's see what the amount here. It's cubic feet per hour, so the amount of rainwater that went in was 76.570 cubic feet. That's it. All right, part B. So, part B says, is the amount of water in the pipe increasing or decreasing at t equals 3 hours? Give a reason for your answer. Now, B is a question where you have a choice. There's an easy way to do it, and if you do it the easy way, it means the later question is going to be more time consuming. If you do it a more sophisticated way, it makes the later part of the question easier. I'm going to do it both ways. The very intuitive way is much shorter, but there's a benefit to doing it the more sophisticated way, but we'll look at both. So if it says, is the amount of water in the pipe increasing or decreasing at t equals 3, some of you would see that and see increasing and decreasing and think derivatives, I need to do an interval test. That's one way to do it. That's more sophisticated. I'm going to hold off on that one. And others of you would look at that and just say, well, why don't we just figure out what's going on at 3? We've got the two rates. Let's see which one's bigger. So what if we just figure out what is the rate the water's going in at time equals 3? And then we can compare that to the rate the water is exiting at d equals 3. And then we'll just know what's going on. It's an easy enough way to do that. Now I've already entered these in on the calculator here. And so for the first one it was 20 sine, and I did 9 over 35. And my value here is 5.086. 5.086. And then I put d into the second function, that negative cubic, and I had negative 0.04 times 27, which is 3 cubed, plus 0.4 times 9, plus 0.96 times 3, and that gave me a very clean 5.4. So if you look at the question, it's pretty clear that the water is exiting faster than it's going in, so the amount of water that's in the pipe at any given time looks like it would be decreasing. And so you could just conclude the amount of water in the pipe is decreasing, and you could say because d of 3, which is the amount exiting, is greater than r of 3. That would be a fair enough way to say that. And if you want to be really thorough, you could just say at t equals 3. Always over-communicate when necessary. All right, so then next part of the question here, now we're going to look at this in a slightly more sophisticated fashion. So now let's look at this and say, okay, what if it says increasing and decreasing? What if I just build the function for how much water is in the pipe at any given time? And this goes back to that concept of we always have an initial amount plus increasing minus decreasing. So I'm just going to put an or right here, and let's pretend you did this approach. And you said, well, the amount of water in the pipe at any given time is equal to 1 plus 2 minus 3. And those aren't numbers, numerical representations, those are items. And we say that is because this is always going to equal an initial amount plus the integral of increase minus the integral of decrease. That's always the template there. So let's see if we can be specific for this function here. A of t is equal to, what is the initial amount? The problem says there's 30 cubic feet of water in the pipe at t equals 0. So it looks like 30 gets trapped in there all the time. And then we're going to integrate from 0 to some unknown time, t, the rate that the water's going in. Well, that was r. And we have to respect the fact that since t is my variable in my interval, I'm going to change this to an x in my integral. You can as long as they're different, you're fine. And then I'm going to subtract the rate that it's decreasing, and that's the d function. So I would say from 0 to t, d of x dt, or sorry, d of x dx. Now, this would be the function at any given time. Now, some of you guys would notice there is no problem putting this in one integral. If you like to do that, you go right ahead. I like to keep them separate because sometimes the time intervals are not the same, and if you keep them separate and you notice you can simplify it, go ahead. But sometimes if you're used to always simplifying it, you'll get tripped up when the time units are not the same. So there's the function for the amount of water in the pipe at any given time, and now the question says, is the amount increasing or decreasing? Well, we're going to take the derivative, and then we're going to find out. So we're going to say, all right, what is a prime of t? Because technically I'm going back here, and I'm going to take d dt of that whole thing. So the derivative of a prime of a is a prime. Derivative of 30 is 0. The derivative of this is very simple, but I'm going to write all of 4 steps. It is r of t times the derivative of t, which is 1, minus r of 0 times the derivative of 0, which is 0. Whenever you take the derivative of an integral, there's always 4 components. Minus, same idea over here, minus d of t times 1 minus d of 0 times 0. So remember, whenever you take the derivative integral, second fundamental theorem, you have to replace the function with the interval values times the derivative of the interval value. Make that show up a little nicer. That's a t. And so that's why there's always 4 points. The function at the interval value times its derivative minus the function at the interval value times its derivative. The fundamental theorem is going to produce 4 values for each time you do that, and because the derivative knocks out the integral. Well, whenever you do this, you wind up getting a really simple function. The 0 is obviously gone, this is gone, this is gone, and we just wind up with this simple function. When is a prime of t equal to r of t minus d of t? That's the derivative of how much water is in there at any one time. Well, if this is our function, then we're going to get our critical numbers, and then we're going to test for increasing and decreasing. So what I would do is I would say, okay, I'm going to set that equal to being undefined. I'm going to set that equal to 0, and I'm going to get my critical numbers. So I'm going to take this, I'm just going to move for the sake of space, move up to the other side here, get rid of this wonderful diagram. And I'm going to say, well, it looks like, once again here, I'm going to do a prime of t is equal to r of t minus d of t. And I'm going to set that equal to 0 and undefined. So when is that undefined? When is it 0? Well, I'm going to get a little more specific here and actually write this down. So it looks like the question becomes, when is it equal to 0? Well, that would be, when does r of t equal d of t? So I would say, when is 20 sine of t squared over 35, when does that equal this other function, negative 0.04 t cubed plus 0.4 t squared plus 0.96 t? Now just make sure, guys, if you notice here that if I set this equal to 0, all I did was add d of t to the other side of the equation, and I'm solving that. And I'm curious, when is this going to happen? Now the other part is, when is this undefined? Cubic functions are never undefined. Sinusoidals are never undefined. So there's no values from the undefined side. So all I'm doing is saying, what I was doing here is I was saying, when does r of t minus d of t equal 0? I added dt to the other side, and that's where I got this. So in order to solve this for t, this once again becomes a calculator question, and I would graph both of these and see where they intersect in the interval 0 to 8. So we're going to once again take advantage of our calculator. We want to do that. We're going to go to y equals, clear out some old work there, and we're going to say, okay, when is the 20 sine of x squared divided by 35? We have this function. And then our other function is negative 0.04 x cubed plus 0.4 x squared plus 0.96 x. Okay, and before I graph it in my window, I'm already going to tweak it and say I'm going to make that just from 0 to 8. And let's see what we get. So there's the sinusoidal, and it's like we're out of our window here. I might have to do a little window adjustment here in just a little bit. And here is our other function here, and looks like they intersect somewhere off the screen here. We're still thinking here, so we're going to have to tweak the window. And so on my window here, I'm going to say, well, my y maximum here, let's go ahead and put that at 30, and we'll see. And we can increase this a little, make this graph a little faster. We'll make that 0.1. All right, there's the sinusoidal behavior, not too surprising there. And then here comes our other function. This is the cubic. Okay. And so once again in the window, looks like we're still thinking here. In the window, we're going to go to, so we have our Y max here. The X max here had a typo there. I just wanted that to be 8 because we're 0 to 8. And yeah, let's go ahead and graph that again. And so you could see it had sinusoidal action, but that sinusoidal behavior really didn't start till after the interval from 0 to 8, which is all we're looking at. And then we've got these little spots here. So it's a little tricky. It looks like it's only got this one spot right here where we're intersecting. And so if you weren't sure, you could actually zoom in a little bit and see, but I'm going to tell you there's only this one spot here. So I'm just going to go to my calculator and I want to find my intersect. So there's first function, second function, and guess. I'm pretty close to the point of intersection. Let's see what we get. Looks like it's giving us 3.272 rounded. Okay, 3.272 rounded. So that's our only value. T is equal to 3.272 rounded. Okay, the only critical number in there. And so we're going to test our intervals. And we're going to say, okay, well, looks like we're going from 0 to 8, and we had one critical number. We'll put it right there as 3.272. Now I want to reframe the question here back to the beginning. Remember, this B is taking a while because I'm doing it two different ways. So B says, is the amount of water in the pipe increasing or decreasing at T equals 3? The short way was just put in 3 and compare. Very short. The longer way, more sophisticated, is build the function for the amount of water in the pipe, take the derivative, get your critical numbers, test your intervals, and then we'll be able to tell. Is it increasing or decreasing at 3 hours? Well, let's just test this interval. If you'll notice, 3 is in that interval. So let's pick a value in the interval, and let's pick 1. I know we could pick 3, we already did the work, but that makes it too easy. So 1 is in the interval, and so I want to see, is that giving me a positive or negative number? And so I could go to here, and I could say, well, I guess since this is my derivative over here, I could do r of 1 minus d of 1, and I can see if I get a positive number or a negative number. And so I would say, okay. And I would say, okay, let's see what we get here. So we're going to do 20 sine, and we're testing 1, so I'm going to put that in the numerator, and I get 1 divided by 35. So that is my r of t value, r of 1, minus left parentheses, and now I'm going to put 1 into the d function here, and that makes this pretty simple because 1 just makes these all the coefficients. So it's minus left parentheses here, and this is negative 0.04 times 1 is just itself, plus 0.4 times 1, still just itself, plus 0.96 times 1, which is just itself. And that is equal to negative 0.748, rounded 0.749, but most importantly, it's just a negative number. We don't really care what the value is, we just care about the sign. And so what that means is, since this was negative, that means the original function here is going to be decreasing. And that's telling me about A prime, the sign, and that's informing me about A. So the fact here that A is negative, A prime is negative, tells me that A is decreasing. Okay? And let's go ahead while we're here, let's go ahead and test a number in the next interval. It'll make the rest of the problem a little easier. So we tested 1, and we got the negative here from decreasing. So let's pick a number in this interval. I'm just going to use 4. That's what I'll test. So I'm going to go back up to here, and I'm going to say, okay, there's 20 sine, and if I put 4 in here, I'm going to get 4 squared, which is 16 divided by 35. And I'm going to subtract left parentheses. So recall, I'm back up to here. I'm trying to see what is the value of the derivative right here. So minus the d function, so minus now left parentheses, and that function is negative 0.04 times 4 cubed, And I just go ahead, even though some of these you know that would be 64, I'm just going to leave it like that. So negative 0.04 times 4 cubed plus 0.4 times 4 squared. And then the last one is plus 0.96 times 4. And that would be that one. And we get positive 1.4. 1.14. We don't really care what the number is, we just care that it's positive or negative, which tells us that this interval is increasing. So, on this approach, the question is, again, B taking a long time doing it this way, what's going on at time t equals 3? Well, we decided to build the function, take the derivative, get the critical numbers, and we tested the interval, and as it turns out, 3 is in the decreasing interval. So, our same reasoning here, decreasing because d of 3 is greater than r of 3 at t equals 3. You could say at this one, you could say at t equals 3, a prime of 3 is negative, so a of t is decreasing. That would be the other approach. Now again, more sophisticated, but now that we've done it, you're going to see how easy, how much faster the rest of the question can go. So let's move on to part C. Very important to understand this even if you don't do it that way and you just did it this way. So these were the two approaches here, the top versus this longer way. Now, part C. At what time is the amount of water in the pipe a minimum? Justify your answer. Well, I think we just figured that out with our critical number right here. So let's pretend, for the sake of example, you did this the fast way, and then you moved on to part C, and you said, when is the water in the pipe a minimum? You would have said, minimums, I need my critical numbers. I'm going to have to build the function, take the derivative, set it equal to 0 and undefined, get my critical numbers, and test them. Well, we already did that. The only thing we didn't do was test a of 0 and a of 8. Now it says, which one's the minimum? Well, if the function is decreasing, there's no way it's a of 0, and if it's increasing, there's no way it's a of 8. But because, just to make sure you get your points, you want to test your endpoints to show you know that. So you can say, okay, well, a of 0, that's going to be the 30. My critical number of 3.272, we already did that. Or, no, we haven't done that yet. We're actually going to calculate that with our a function, which is over here that we built. And then we're going to compare that to a of 8 at the end of the day. Okay? So a of 0, we already know the answer because we did our interval test, but we have to justify it by testing all of these. So we're going to go back to our calculator, and we'll put this whole thing in here, and we'll see. All right? So what I'm going to do is put in the whole a function back over here. And I'm going to say, well, this is 30 plus the integral from 0, and I'm going to go to 3.272. So 0, whoops. Clear that out of there. Okay, 0 to 3.272. And I stopped as at 3 decimals. You can enter as many as you like here, but I think for this type of question, we're going to be we're not going to need the extra decimals because we're only comparing these 3 values, and they're pretty far apart. And now we have the function r, and so this was the 20 sine t squared over 35. So we have x squared divided by 35, and there's that function. Now, because these functions right here are the same interval, I'm going to go ahead and put in the d function into here. So I'm hoping that doesn't confuse you. Because the interval is still 0 to 3.272, I'm just going to go ahead and do minus, and then I'm going to put in the next function, which is the d of t. And so the d of t function is, you got to make sure you keep track of your negatives here. It's minus a minus, so I'm going to put in my negative here. Minus 0.04, and that is x cubed, and then plus 0.4 x squared plus 0.96x. All right, and then we have the other parentheses, variable of integration here is x, and let's see what we get. 27.965 rounded. 27.965. Okay. And now we're going to figure this out at the very end of the day for 8. So I'm going to take advantage of editing here. Just went through, and now I just entered what I last put in here. The only thing I have to do now is go up and replace this 3.272. I'm just going to clear that and just put in an 8. That's that easy. 48.543. And rounded 48.544. Okay, so back to the question. It says, at what time in the interval is the water in the pipe a minimum? We already knew it was this from our interval test, but we tested each of them, and sure enough, you can see the minimum is occurring at our critical number, 3.272. And so we'll just finish that off by saying minimum amount of water is in the pipe at time equals 3.272. And I'll put yielding 27.965, and our unit of measure is cubic feet. Cubic feet of water. And they actually just wanted to know the minimum, not even the amount, so there it is. Okay, so all the work there on part B wound up making this shorter, and if we wouldn't have done it, we would have had to do it. Okay, then part D says, the pipe can hold 50 cubic feet of water before it overflows. So after 8 hours, it's backing up so much it's overflowing. And so after 8 hours, water continues to flow into and out of the pipe at given rates until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. So when does our amount equal 50? Would be the question. And once again, you guys, we go back to here and we say, oh, it's this amount equation. This was a really important equation right here. That's the amount. And what happens when the amount is 50? When the amount is 50, that'll give us when it's overflowing. So what if we just said, well, I'm going to write more than I need to here. But I have a of t is equal to 30 plus the integral from 0 to t of r of x dx minus the integral from 0 to t of d of x dx. Okay, capital D of x, I should say. And again, I know some of you are noticing here, you could write that in one integral, no problem. So this is our amount, and what they're saying is when the amount is 50, when that's 50, we don't have to solve this, but write an equation that would, it says in the question, it says, solve an equation involving one or more integrals that gives the time as W when the pipe will begin to overflow. Well, if you'll notice here, you guys, we have t as our time value, and x is just our variable of integration. So they want the t value to be the w value. So all we have to do, it's this easy. You just say, oh, well, I guess it'll be 0 to w r of x, or you could make this t now. It's up to you. It doesn't matter. But we'll say, okay, well, that'll be t dt if you want, minus the integral from 0 to w of d of t dt. And again, you could have left those x's. It doesn't matter. So all they're saying is this amount equation, why I took the time to do it here on B, is it winds up being very important. You have to use it for C, and you actually have to use it for D. And that's why. So there is the final answer for D. Here was our answer here for C. And we had solved A twice here. Or, sorry, solved B twice, which was right there. It's decreasing. Or we did it that way there. And then A was a very straightforward answer right there with an integral. So another two-rate style question, 2015 number 1. You have two rates, rate in, rate out, and an initial amount. We just manipulated it. Integrated the rate in to figure that out. On this one, we compared what was going on at time equals 3. We did it the easy way. Then we did it the sophisticated way, writing our amount equation, which is typically the most difficult and the most rewarding part of the problem, point-wise. and we showed doing it both ways, getting a critical number, testing our intervals, and we wound up using that to discover that was the minimum. But you have to demonstrate that you tested your endpoints here for part C as well, and we got the time where we had a minimum. And then we just set the amount equation equal to 50 and change the variable to t, from t to a w. And always make sure you don't have that same variable there. That's a no-no. Okay, 2015 number 1. Thanks for watching. We will see you next time.